Hey folks, in this video I'm going to make an attempt to try to briefly summarize all of our hypothesis tests into a concise video overview here. So the goal of this video is not to tell you every detail about these tests, but provide you possibly with a flowchart of sorts that will help you distinguish among these tests and when you use them. I've got them sort of color-coded here for our viewing pleasure, and I'll try to sort of stick to that when I write these up. Essentially, the type of test that one may choose to use is going to be dependent upon the type of data that is being analyzed from the variable or variables that were measured, right? So we've got quantitative versus categorical. And then also the tests have certain requirements, and are the requirements met? If not, what can we do? So let's dive in. First, I'm going to detail what chapter you can find this information in our textbook. So over here in orange, this was in chapter 7. In green, when we went to paired data, that was chapter 8. Over here in yellow, when we moved to categorical data, that was in chapters 9 and 10. ANOVA was chapter 11. And linear regression, it's actually about the slope, but that was in chapter 12. So I'm going to go chronologically as well, which is also sequentially across these chapters. So in orange, chapter 7, the two-sample t-test was our first hypothesis that we were introduced to. And here we've got two independent samples. By independent, I mean not paired. They were independently selected. The response variable that was measured was quantitative. So I'm going to say response variable, which is a random variable, needs to be quantitative. And we saw a lot of examples such as length of fish or angular hours in a day. But the two samples that are being compared are distinguished by a categorical variable. So for instance, we compared the lengths between different species, but the response variable was quantitative indeed. So the hypothesis test, well, we're in orange here, so this is the two-sample t-test. If the requirements are met, if we can't use the two-sample t-test, we do have a backup test, but let's talk about the requirements first. I'm going to number these as well. So number 1, in no particular order really. Remember, we need random sampling, or the data needs to be the result of a randomized experiment, or randomized experiment, right, where the experimental units are randomly allocated to their treatment. Second bullet here, we need independent observations. The length of one fish does not influence the length of the next fish, things like that. And 3, this is the doozy, because these first two are a result of the study design. Number 3 here, this is inspection of the data and whether the data meet the normality requirements, right? So I'm going to say normality, where we need to test if the data came from a normal population. Remember, we did that with the Shapiro test. But we also had our backdoor by using the central limit theorem. If the sample size is at least 30, then that means that the corresponding sampling distribution can be considered approximately normal. Okay, so those requirements need to be met. If they cannot, then our backup test is to use the Wilcoxon Mann Whitney test. So if number 3, that's over here, number 3, cannot be met, or satisfied, then we can use the Wilcoxon Mann Whitney test. And remember, we want to try usually to meet these requirements, the normality requirement, if possible. So there are other tricks up our sleeves, right? Like we can try to meet this normality requirement via transformation. Try to achieve via transformation. We saw log and square root. Right, so if you cannot meet the requirement for normality in some way to do the t-test, the two-sample t-test, then we've got our backup test, which is the Wilcoxon Mann Whitney test. Okay, so check mark, check mark. Let's move on to a brief sum up from Chapter 8. I'm going to refer to these requirements labeled 1, 2, and 3, so I don't have to rewrite them all the time, just so you know. Okay, so paired t-test and the Wilcoxon Signed Rank test. What type of data do those tests apply to? Well, again, there are two samples, but they apply to paired samples where there's some sort of matching or natural pairing that occurs, possibly before and after, or maybe sibling pairs. Again, the response variable is quantitative, and if we can, we want to use the paired t-test. Because it is a t-test, it requires all these same requirements as what was listed up above. So just to be clear, these all apply to the t-test. So I'm going to write that the requirements here are same as numbers 1, 2, and 3, but remember, with a paired t-test, it is basically just the differences that get utilized in the analysis. So this is the same requirements, except that they need to be applied to the differences. Oftentimes with the paired t-test, due to those differences, you often get negative values, and so transformation can be tougher because we don't generally square root or take the logarithm of negative values. But again, sort of that same process applies if this third requirement, which is that the differences need to pass this normality test, or there need to be at least 30 of them. If number 3 can't be met, then the backup test is another Wilcoxon test, but its name is the Wilcoxon Signed Rank test. So sort of the process here, we've got the t-test as our primary go-to for comparisons, but if we can't meet its strict normality requirements, we've got the backup, the Wilcoxon style test. They have slightly different names, so caution there. So we'll call that a day on the green for chapter 8. We will move to the yellow zone here, which was where we talked about categorical data. So the type of data here is about to take a shift. In chapter 9, the first hypothesis test for categorical data that we saw was applied to the proportion. And so this is called the one sample proportion test. Sometimes it's called the z-test for the proportion z-test, because it utilizes the z distribution and not the t distribution. So embedded in the name one sample, there is only one categorical sample, as opposed to 2 samples up here. And because it was related to a proportion, we could call these a dichotomous variable, right? Where based on a binomial situation, right, either something occurred or it did not, dichotomous. Using a normal distribution for proportions requires that its sampling distribution is also normally distributed, and that is generally accepted if these 2 criteria are met. That's n times p and n times 1 minus p are at least 5. And by p, here I've got a little subscript on there. That's actually the value of the proportion in the null hypothesis. So that one's pretty quick there. The next item on the yellow side is the chi-square goodness of fit test. Chi-square goodness of fit test. And that applies, again, when there's only one categorical sample, but there are many categories, right? It's not just 2 categories like succeed, fail, but there are multiple categories. And so here we needed to also have another piece of information where we wanted to compare the frequencies that were observed for each of those categories. We needed to compare that to a set of proportions, right? It was a whole distribution. So there's only one sample that composes your response variable. It's the categories that were observed. But you compare that to some other distribution which has proportions or probabilities expected for each of those categories. Here, the requirements, we still need random sample and independent observations, but this test requires all the expected values to exceed 5. Not too shabby. The next yellow test on our list is the chi-square test of independence. No longer does this pertain to one categorical variable, but two? And in a previous video, we highlighted how that can occur. It could be one sample with two variables observed. It could be two samples in which each sample has one categorical variable measured. So there's different intricacies there, but this video is not about those intricacies. These expected values from the goodness of fit test were determined, you might recall, by n times p. And the chi-square test of independence has these same requirements as the goodness of fit test. So I'm going to be explicit. 1, 2, and all expected need to exceed 5, comma. But here the expected values, you might recall, are the row total, the column total over the sample size. I think I can do it like that. Okay, so we did not discuss a backup test for the goodness of fit chi-square test. However, we did for the test of independence. If the expected values are less than or equal to 5, then we can use Fisher's exact test. Usually the data for a chi-square test of independence is presented in what we were calling an R by K contingency table, right, where the first variable has R categories, the second has K categories. Usually the Fisher's exact test generally is applied to 2x2 tables, but that was the only context that we saw those anyways. Okay, so scrolling up here, we check on this yellow portion. Next up, let's briefly discuss the context in which we utilize ANOVA. Now, there's actually different types of ANOVA out there. This is one-way ANOVA. We kind of kept it basic for our course. We connected analysis of variance as an extension of the two-sample t-test, where when you only have two groups to compare, the two-sample t-test is the way to go. However, if you've got 3, 4, 5, or more groups, then ANOVA is basically the method to use, so it's an extension of the two-sample t-test. As such, analysis of variance has essentially the same requirements and applies to the same type of data. Let's formalize that now. One-way analysis of variance is applied to generally 3 or more independent samples, and we use the letter I to represent the number of samples, and generally that is 3 or more, so I is greater than or equal to 3. And the response variable, of course, has to be quantitative if this is an extension of the t-test. So the requirements for ANOVA, as already mentioned, the I samples must be independent from each other. Furthermore, the observations must be considered random samples from their respective populations. Just like the t-test, the population must be considered approximately normally distributed. So really nothing new so far, random, independent, normal, but there is an additional requirement that the standard deviations for the groups must be approximately equal. So the population standard deviations are approximately equal. So if there are I groups, the first group's standard deviation needs to be approximately equal to the second, approximately equal to the third, fourth, etc., to the ith group. In our course, we did not discuss how that is verified in detail, so we're going to kind of just swim past that. However, that is a criteria for the validity of ANOVA. Last on our list of hypothesis testing techniques that we have seen was embedded within linear regression. And this was actually a hypothesis test regarding the slope, right? Where the null hypothesis is that there is no linear relationship between x and y. So this was a little different. Here, this concerns bivariate data, x and y, that are both quantitative. And recall that the bivariate data form ordered pairs that are considered coordinates, x, y. Now, the conditions for our inferences regarding the slope to be valid, again, we have random sampling involved. There's a couple ways that can be achieved. The pairs x, y must be independent, same as earlier, and not use any matching. So the ordered pairs are independent of each other. So x1, y1 is independent of x2, y2, and so forth. Just as before, there is a normality requirement, but it is applied to the residuals. Residuals are approximately normally distributed. Lastly, because we are working with linear regression, linear models, it's required that the data itself follows a linear relationship. As such, these residuals should not have any patterns, and that often takes shape as such that they have a constant standard deviation, constant spread or variance. So linear regression, as we've discussed it, is more about the relationship between x and y, between the bivariate variables here. Whereas all of the above hypothesis tests are about comparisons. So it's a bit of a different perspective with linear regression. That's going to do it for this video. It was as brief as I can make it, but hopefully that does a quick sum up of the applications for the different hypothesis tests we've covered in our course.